in Talk Best. Okay. So hello everyone, thanks for coming. Today we have a talk by Professor Nuno Sá, who's going to talk to us about ambiguities in Noether's theorem and how to fix them. So thank you very much for accepting our invitation, and please take it away.
Hello. So I'm going to talk about Noether's theorem because I recently came across some features of Noether's theorem that I was not aware of. I think that perhaps, like many of you, I was very much impressed when I learned Noether's theorem as a youngster. And you know, the connection between conservation laws and the more abstract principles such as symmetries impressed me very much. And then a long time passed by, and then now I came across a few features of each which I had not realized. Well, first of all, let me recall that Noether's theorem works for systems whose dynamics is determined by an action principle. So it is built in this the proof of Noether's theorem. It requires an action. So I sketched here a brief recollection of how Noether's theorem is proved. I did it in a most simple way, using here, an action which depends only on time and on the first derivatives of the field. And then you have these, you make small variations of the fields and of time. And then you go through this calculation. I don't think I should go through it again. In fact, I asked some students before, and they told me that they had learned this at their courses. So the thing is that you end up with this variation here, the variation of the action. Here we are not doing anything, we are just computing the variation. And then you get these two terms. You have here a total derivative, and you have this term which is proportional only to the variation of the field variables. So now from this result, you can take two consequences. One is that if you fix the variations of the fields, or of the dynamical variables, in this case x, and perform no transformation in the evolution parameter, then you perform this variation with the variation fixed at the extremes of the action, of the integral of the action, then this is a boundary term, it does not count. And because this must be valued for all variations, then this integrand must be zero. And this is a standard way of deriving the equations of motion, which are here, Lagrange equation, okay? Now, from this result, one can also derive Noether's theorem, which one now will not fix the variation of the dynamical variables at the boundary, let it change freely, and allow also for the possibility of changing the evolution parameter. And if this is a symmetry of the system, then this variation must be zero. And therefore, this integrand must be zero, okay? This part here is what are the equations of motion. Oops, I just moved. What happened? Sorry. So I will call it just this psi, like Noether did in her original paper. So we end up with this thing, which is the main result. If the action is invariant for certain transformations, then, and here I wrote moreover the transformations in this form, imagine, I'm just simplifying this. I mean, Noether did it, in fact, in full general mode, if you read her original paper. But here I'm just simplifying just to give an idea. So if you have here a variation in x, which goes with a small parameter epsilon, and in t likewise, then you get this. This means that because this is proportional to the equations of motion, it means that on shell, this has got to be a constant if the action is invariant under these transformations. Okay, now we can give the two simplest examples. If we take here f equals to 1, the variation in t is just proportional to this epsilon, and the variation in x is 0. So this corresponds to time translations. Then you get that this quantity must be a constant, and you can recognize this as the energy. In fact, the symmetric of the energy, okay? And in the other case, space translations, we get this, which is just a conservation of linear moment. So this is the famous connection between symmetries and conservation laws. As I said, Noether did this in a most general manner, considering field theory, that is not only one parameter in the integrand, but in space-time, and considering several fields, depending on an arbitrary order of that the Lagrangian could depend on not only on the first derivatives of the field, but up to order n. Of course, to write those formulas here would be, occupy much space, but you can see it in her original paper.
Steve,
Hmm?
sorry to interrupt. What about dual gauge theories, for example? They do not admit an action principle? They do not admit the Lagrangian? Do they obey Noether's theorem?
No, of course not. If they are not derivable from an action, they do not obey Noether's theorem. That does not mean that there are no conserved currents. Noether's theorem states that if the action is written in the form, is the integral of the Lagrangian density, and is invariant under a certain transformation, then you get a conserved current. Now, if you cannot derive the action from the equations of motion from an action, that does not mean that there are no constants, no conserved currents. So, and in fact, I know that there are people who have studied that, which are the conditions that must happen for there to be conserved currents. I don't know exactly, but I know that it doesn't, I mean, it doesn't exclude, precludes the possibility of existing conserved currents, okay? Even if the action is not derivable from if the equations of motion are not derivable from an action.
Excuse me.
Mm.
Let me point out that you have to implement the symmetry you want in the action. Once this is done, then the Noether theorem says that there is a conserved current. If your theory, if your action is invariant under gauge transformations, then you could use Noether's theorem to find the conserved current, and you'll find out that this is the conservation of the charge. So the issue is how do you implement the symmetries you want in the action you think describe the phenomena you are interested in. So so you have to introduce the symmetry in order to find the conserved current.
Yes,
but I think the question was in case the equations of motion were not derivable from an action.
Yes.
Because you can write equations of motion which are not derived. I think as what I understood from the question of the student was this was the question, wasn't it?
Yeah, self-null theories cannot, one cannot write an action, a Lagrangian, but you can impose the symmetries at the level of the definition of the field by its Hodge rule.
In order to have...
Oh, okay, but another theorem applies only to actions, to equations of motion derivable from actions. So, as I told you, I don't know how does it work in that case, if there is any corresponding theorem. But if you want to use another theorem, you need a Lagrangian, okay?
Thank you.
Okay. Now, here is, so this is the extension. I actually wrote just for you to see how does it work. If you have for a field theory, okay, depending up to second order in the fields. So you end up with these equations of motion following the very same procedure that we just did. And we end up with this main result again, that you have that this combination of the equations of motion is equal to a total divergence, okay? And then this, I just wrote this to show you the standard result. If you consider variations like this of your space-time variables and infinitesimal variations like these of the fields, then you get this, that there is the divergence of this quantity is proportional to the equations of motion. And this quantity is given by this formula. Here is written up to second derivatives of the field, but if you eliminate these second derivatives and write here the, for instance, this where the fields do not transform, this is not a gauge transformation, you only have space-time variations, you end up with the standard formula for the stress energy tensor, okay? So here are a few examples. Here I write the Lagrangian for electromagnetism coupled to the Dirac field. You get these equations of motion here, and then the variation of the Lagrangian is this, okay? And from this, now you can apply, you know that this Lagrangian is invariant under these gauge transformations, okay? The standard gauge transformations for electromagnetism. You will apply them in infinitesimal form, plug them in here, and then you get this equation, okay? If you define this quantity here, that you may recognize as the current, then this equation becomes this set equal to 0 becomes this, okay? And you can develop this and end up with this final equation, which is the core of Noether's theorem. The divergence of the current, there is a quantity, a current, whose divergence is a combination of the equations of motion. So it vanishes on shell, okay? This is the core of Noether's theorem. So now I made a few slides here with questions that I want to put you, because I remember that when I studied Noether's theorem as a undergraduate student, there was one question that I asked myself, which is, if you have gauge invariance, you have one current that is conserved. Now, if you have, besides global gauge invariance, if you have local gauge invariance, then apparently you have infinite gauge invariances possible, because you can choose a function from point to point. So wouldn't we get much more conserved currents? Because you have, in fact, infinite transformations that leave your action invariant. Now, in fact, we can see from this previous calculation that the derivatives of the gauge parameter, in fact, disappear. And we end up only with this, okay? only with this multiplied by alpha, then alpha cuts. So the same current is obtained for all gauge transformations. So, and this is one thing that, so this answers my question. Even if you have a global gauge transformation, you still get only one conserved current.
But excuse me, what do you mean by infinite symmetry?
I mean, if you have one, imagine you have a global gauge transformation, okay? You have, let us say, alpha equals 1, okay?
Yes.
But you can have alpha equals to sine of x, okay? You can have any function, right? If you have point...
but the finiteness of the transformation has to do the number of generators the transformation has. And if you put f of x, it has still one single generator, and it's a finite dimensional symmetry. Infinite dimensional symmetry would mean that you have an infinite number of generators. And it's not what you have explained us, okay?
Okay. Yeah, well, maybe that is why I put this question. Maybe that is the answer. What I meant is that if you have a global transformation, that is one transformation.
Yeah,
and
so
you
I
have
understood your point, but you see a gauge transformation, if the symmetry group is U1, right? So is a finite transformation. Okay, if it's is a finite group, is a finite transformation. It has a finite number of generators, and you can generate all transformations from a linear combination of the generators of your group. So
yeah, the thing that confused me a little is that in fact here you have one group acting differently at each point of space-time, right? If you have a global transformation, the element of the group is the same at each point of space-time.
but it's well, that's
but maybe the core of the solution is there. I was not presenting the solution. I was actually putting this problem, you know, because, but maybe the source of the explanation is what you are telling. I don't know, actually. I was putting this question.
Well, as far as I understand what it's all about. The finiteness of the group, which means the finite number of generations of the group.
Yeah, okay, maybe that's the point. Okay. Now, what else I was going to talk about was about this thing that also many people is not aware of. If we pick, if we do Noether's procedure to find the stress energy tensor of the electromagnetic field, you get this expression here. Now, this you can see that this is not the familiar expression that you are used to. This is not even gauge invariant. That was done applying, you know, like this translation symmetry, such that delta x is a constant. So this is when we should get the energy momentum tensor. The problem was identified by this guy, by Basil Hagen, a long time ago. I think he was contemporary of Noether, that this happens because translations and gauge transformations do not commute. And he found a way that he had to introduce, to combine space transformations with gauge transformations in order to obtain a gauge invariant result. And he found out that if you perform these two transformations together in space and the gauge transformation such that the gauge parameter is given by precisely this value, then you get the right result for the energy momentum tensor. So this was just one point one thing that I was pointing out about the subtleties of Noether theorem. But here, this is a more important...
Excuse me. Could you get back to the previous slide? Well, when you see the first energy momentum tensor, the one is written at the top. So it's not symmetric, right? And the energy momentum tensor should be symmetric. That's
right. It is not symmetric.
Yeah. So the issue is what type of terms I have to add on in order to make the energy momentum tensor symmetric. Obviously, because you have the electromagnetic Faraday's tensor, the obvious thing is to consider an addition of symmetry, gauge symmetry. But the recipe for a general case would be look for extensions of the energy momentum tensor, which is symmetric. It might be not sufficient for a very general case, but it works in most of the cases. In the case you presented, obviously, there is a U1 gauge symmetry, so you implement it, and this does the job.
Yes, in fact, particle physicists mostly use a procedure by Bell-Infant, which is, it is what you are saying, introducing extra terms, but it has a prescription for that. Actually, I do not like very much Bell-Infant's method. I think that it seems a bit arbitrary. The method of Basel-Hagen is very definite, in my opinion, and goes to the point. One can do that. One can just check if there are, and there are always, as far as I know, in particle theory, always terms that you can add whose divergence is zero off shell. You can add such terms in order to make the tensor symmetric, okay? And that may fix the problem of gauge invariance in this case too. It does, if you use Bell-Infant's method here. But well, anyways, my point here was to call attention that you just don't use another theorem as a recipe, you know, because you may get the wrong result. In this case, there are these two famous methods by Bell-Infant and by Basel-Hagen. I personally prefer the second one, but well, that's why I didn't mention Bell-Infant's method. Yeah, but well, the point is that you don't get it straight from Noether's theorem, you know.
Just to point out that there are many situations on which you do not have gauge symmetry. For instance, in fluid dynamics, you have an energy momentum tensor, right? And you do not have these elementary symmetries, and therefore the method is to look for something which is symmetric. Okay, so it's not always that you can implement a symmetry like the one you have implemented. Okay, so that's
yes, yes, but that is related with, in fact, with my second point, which type of terms we can introduce. So that is my second example using the Klein-Gordon equation. So you see here that the Klein-Gordon equation, this is the standard way of writing the Lagrangian, but you can perform a partial integration and get the Lagrangian in this form. Okay. They produce the same equations of motion because they differ only by a surface term. However, they produce different energy momentum tensors. If you follow Noether's recipe, the standard energy momentum tensor is this one. But if you use this other Lagrangian, which differs from this from a surface term, you get a different energy momentum tensor. So, okay. So I actually did, for fun, one thing which I constructed a wave packet of Klein-Gordon wave packet and plotted it. Here you have, it is moving to the left. At an instant it is green, at another instant it is blue, okay? And then I computed the energy using the two energy momentum tensors. But what you see, it's very difficult to choose between these two tensors they are both symmetric. They are both, they both have positive energy. So we don't really have a much of a way to distinguish, to have a criterion to exclude one of them. So I computed the energy, and then I got this. This is for one and for the other. Green here, and then after an instant, it is here. Here it is green, after an instant, it is here. Let me ask you, which one do you think is the standard energy momentum tensor? This plot is for the energy only. This is, I don't know if anyone wants to give a try.
I'm sorry, but what are you plotting exactly? The energy as function of?
The energy as function of position. Here
Okay.
in the horizontal axis is position. And this is 1 instant, the green, oops. The green is 1 instant and the blue is the next instant.
Okay, good.
I don't know if anyone has a clue.
Well, I teach my students that when you have doubts of this type, you should use another trick. The trick is to couple with gravity, because gravity allows you to get the energy
Yes.
denser.
Also, we will go that. I'm going to talk about that in the end.
Okay.
And I also have a question for the, for the students about that.
This would do the trick. Okay.
But here the question is, between these two tensors, which one is the? I can tell you that the number 1 is the one that comes out from general relativity. If you use that trick that you are telling.
You couple it with gravity.
Yes, if you couple to gravity, this is the one that
comes out. Yeah.
Yeah. But the thing is that we are not talking about gravity here. Okay, this is flat space. I'm doing Klein-Gordon field in flat space. And you have these two tensors. And surprisingly enough, I can tell you that the standard one is the one which has all this variation from point to point. This very smooth one is the new one that I constructed. So, but as you can see, they are both positive, and they all have a total energy which is equal. Because, well, you will see then later. I didn't show that slide yet, but the total energy of is the same for them. Here I have the same plot for momentum density. Again, the one that wiggles is the, let us say, the real one, and the left one is the fake one. Okay. And the total momentum is again the same if you integrate both. And these things about being able to choose different energy momentum tensors, apparently there are other people who are aware of that and even use that. You see this paper by this renowned gentleman, they do precisely that. They say the conventional energy momentum tensor does not have the properties that we desire in order to quantify. So we are just going to switch the conventional tensor by this tensor, which is a combination of the two tensors that I showed before. Okay. So this actually exists, and our people, such an ambiguity actually exists. And here I did, oops. Here, this is another example of such an ambiguity. I constructed this model, which is a Lagrangian, which is gauge invariant, as you can see. These are fixed tensors. So this is not invariant under space-time transformations, but it is gauge invariant, okay? So if it is gauge invariant, there must be a conserved current. We can check the equations of motion are here. As you can see, they do not involve the tensor A, which is anti-symmetric, and the S is symmetric. Because you can see that this, in fact, is a boundary term. So the equations of motion only involve S. But when you compute the charge, and here we are not talking about energy momentum, we are talking about an internal symmetry, the charge depends on A, okay? So there really is an ambiguity because this, whatever the value of A here, the equations of motion are these. So any value of A should reproduce all the physics contained here. But when we apply Noether's prescription, A shows up. Okay.
Yeah, but,
boundary terms show up.
Sorry, your Lagrangian density doesn't have. Well, the first term is not obviously symmetric. Should have another term on which you switch phi bar with phi in order to be symmetric, and this would mean that in the second term you should have a minus term like that, so that is antisymmetric. That's what you mean?
I beg your pardon.
So I look at your action, and you told us that S mu nu is symmetric.
Yes, this tensor is symmetric.
Yeah, but this symmetry is not obvious from the Lagrangian because if
it is by definition.
Yeah,
this is not a matter.
Nu in the kinetic energy term, it doesn't look symmetric.
No, if you construct this Lagrangian and this function, you define it to be symmetric. Okay, you just plug in there a fixed symmetric tensor. It can be, for instance, the delta function. Okay, and here you plug an anti-symmetric tensor. Okay, and you can check that this gives a real action. You can compute the complex conjugate, and this is real. Okay, so that's why you get proper equations of motion, and then you just follow Noether's prescription, compute the current, and you get this.
Yes, I'm confused. Do you see? If I change mu per nu, right, I get S mu nu is invariant. It is symmetric. But the other term is the derivative of nu with respect to tau for phi bar, and the other with respect to 5. So it doesn't seem to be the same term, is it? You say you change it again, and it gives back the. Okay, so this is okay. This is fine. Yeah, sorry. But the other one,
I mean, if you put here, this is gauge invariant. If you put here a global transformation, you see that the derivatives do not act on a global transformation.
I mean that it would be better to put the symmetry and the antisymmetry in the action. I mean, so that's what I mean. Okay. The first term doesn't matter, but the second one it does. Okay, but
you know, if you have a global symmetry, the transformation goes out of here. As long as you have a complex conjugate of the other, the global transformation will cancel. So this will be invariant, whatever the rest is.
Well, the terms are different. I mean, derivative of nu of phi bar is not the same than derivative with respect to mu of phi bar. Okay.
No, it is not. But under a gauge transformation, well, I don't know how to write here, but under gauge transformation, you just have an E exponential of I. Here you have exponential of I alpha. And here you have exponential of minus I alpha. And because these are global transformations, they go out of derivative and they cancel each other. So this is indeed invariant under global transformations.
Well, that's fine. I mean that it's not obvious that this term is antisymmetric. That's what I mean. Okay.
But this thing is antisymmetric by definition. Okay. You construct here something put here. It's not a consequence. It's the definition. It's here. I define S as symmetric and A as antisymmetric.
Yeah, but by definition, it should be minus the initial term that you have written, okay? And if I change mu per nu in the derivative, it's not obvious that it's the same. because they act on a different phi. Okay, but as I say,
Well,
it would be better to write this explicitly, but okay, I take your point. From the gauge symmetry point of view, it's the same, yeah.
Okay, so this was just another example, and to show that this problem is not associated with space-time symmetries. You can have this ambiguity in Noether's theorem. In fact, I made the calculations, and if you have, I just did it for a term like this. If you have a surface term like this, okay, where this depends only up to the first derivative of the field, then you can compute the Noether current for this boundary term, and it is this one. You see that if this is symmetric under transformation, this will be 0, okay? And then you can see that this is the derivative, this current that shows up inside here, this current that shows up here is in fact the derivative of, the current is all this, I'm sorry. This is the current that you define. This is the derivative in an anti-symmetric tensor. So if you have a boundary term, it produces a current term, which is the derivative of an anti-symmetric term. That is why it's automatically, its divergence is vanishes off shell, okay? But because it's just a mathematical identity that the divergence of this is going to be 0 because this is anti-symmetric. But you can see that this is anti-symmetric, okay? These tensors are anti-symmetric, both for space-time transformations and for gauge transformations. So the ambiguity is associated with the presence of boundary terms. And in fact, some people call, if you read in the literature, people call this the superpotential that you can add in order to create different Noether currents. So we come to my question 2. Is there a criterion for choosing the right Lagrangian? In fact, or for choosing the right energy momentum tensor, as Professor Orfeu said, there is one such criterion, if, for instance, for the energy momentum tensor, if you couple it to gravity, and we will talk about that in the end. But besides that criterion, let us say, is there a criterion for choosing the right Lagrangian and consequently the right energy momentum tensor or the right charge? This is related with the question whether energy and charge are actually localizable. Because if there isn't such criterion, we can compute the global integral and know that if for an object which is in a region of space, it has a certain energy, a certain charge, but the precise localization of that energy and charge within the object cannot be set if we do not find an absolute criterion to choose. You know, like in this example, where is the energy? The total energy is the same, but different tensors provide different distributions of the energy within the wave packet. So this was my second question for you to think.
Excuse me, I'm sorry. Can you go back to the action with the symmetric matrix and the anti-symmetric? I just have a quick question. That anti-symmetric term, that two form, is it exact? Because if so, then there's a U1 gauge symmetry, which means that Lagrangian is not gauge invariant, and the U1 generated by that two form. So
I didn't understand quite well your question. I mean, for me, it is quite obvious that this is gauge invariant. Because gauge invariant.
Under what?
Huh?
Gauge invariant under what? Under the U1 symmetry generated?
Under the
where the field strength is
U1
AU?
symmetry, this is a complex field that transforms like phi goes to phi times the exponential of I times a certain number.
Yeah,
That's the standard.
That's a global symmetry. That's different.
Yes.
A global symmetry.
A global symmetry.
Just global, yeah, but
Yes.
not a local gauge symmetry.
If you have a two tensor and it is exact, then it must be written as a derivative, an anti-symmetric derivative of some gauge potential, which means that your first term, the S mu is not gauge invariant under that symmetry.
This term?
Yes.
But again, you have here the complex conjugate of this. The group transformation of one will cancel the other one.
No.
It seems rather obvious to me.
Yeah, this is just global gauge symmetry.
Yeah, that's a global symmetry.
If it were local, you had to introduce a covariant derivative, which is not the case. No.
No,
yes,
it is the case because you have a two tensor there. But it's not doing.
I'm not quite understanding your question. Professor Orfeu said, and is right, this is not globally invariant.
Yes.
But it is,
global,
I mean, locally invariant, but it is globally invariant. And that's all you need to compute a conserved current. Global invariance. You don't need local invariance.
Okay. No. There's a gauge symmetry generated where the field strength is A mu. That's what's happening here. Then you have to yes, you need covariant derivatives if you define an anti-symmetric tensor to couple that thing over there, the delta mu, and then immediately there's a U1 gauge symmetry because you can always define it, assuming it is exact, of course, that it can be written as an exterior derivative of a one form, and which is invariant under U1 gauge symmetry. So your covariant, your partial derivatives must be covariant derivatives under that symmetry, which means that the Lagrangian by itself cannot be consistent.
Yes.
I don't know if I'm frankly not understanding your argument.
Philippe, this is a global symmetry.
Yes. Yes.
Yeah, if you ask me, this is very instructive. I have my doubts, but indeed, if it were a local symmetry, you should have a covariant derivative.
Yes.
One form
I agree.
support your symmetry. Yeah.
I'm just saying that if you write a term an anti-symmetric term that couples, immediately you're forced to introduce a gauge symmetry. Just because that A mu can all, if it's exact, then it's written by like a field strength tensor.
Yeah, I agree. Yeah, that was my original doubt. Yeah, I agree. Yeah. Yeah, you should have introduced in your action the symmetry in both terms, to make explicit the symmetry in the first term and the antisymmetry in the second term.
Yeah, and A mu immediately generates a U1 gauge symmetry. Not only do you have a global U1 symmetry, you have a U1 gauge symmetry.
I don't know if I understand correctly. You are talking about an issue of notation. You believe that I should have anti-symmetrized this term and symmetrized this term. Is that the issue?
No. I'm saying that I'm saying that if you have A mu and you write it as d mu f mu and anti-symmetrize it, then you have a gauge potential immediately. So you not only have a global U1 symmetry, you have a gauge symmetry. My point is that if you introduce a two form in your action to couple with your kinetic term, then you're introducing extra symmetries, and your Lagrangian must be invariant under those. It's not only the U1 global symmetry, but the U1 gauge symmetry is also included there. And the first term stops being invariant.
Well, what Philippe is saying is that, you see, this A mu is antisymmetric, so it should couple with something which resembles the strength tensor of electromagnetism, which is point invariant. Okay.
Exactly.
Yeah. So
I don't know if it makes you more comfortable. One could write here
Yes.
d mu,
I wouldn't
d
feel
mu
comfortable.
minus d mu, d mu. I mean, it's divided by 2. That's the point.
No, because if you do write that, then the first term with the symmetric term, then it stops being invariant, gauge invariant. That's my point.
I think, Bruno, I think that you are trying to complicate something which is extremely simple. I chose this toy model precisely because of its simplicity, such that you don't need any algebra to understand it. All you need is elementary calculus from the first year of undergraduate studies. You know, this is just a sum in these terms, and this is a tensor. You can write this one, you can define to be 1, 0, 0, 1. And this one you can define to be 0, 1 minus 1, 0, for instance, and that's done. And then you just plug in, you can check that it is real, this action. And then you can plug here the gauge transformation, it goes out of the derivatives, and it is invariant. You don't need really any sophistication to understand this. It's the most simple that you can look at, you know. I think that sometimes people learn too much theory and complicate things which are very simple. This is
the point of Philippe is well taken. Obviously, we're talking about a global symmetry, and the global symmetry is not, let's say, very instructive, okay? Because, well, we know that symmetries are local, okay? But anyway, your example, okay, I think it's consistent in the sense that one can see that in your current, you have always the product, if I read it correctly, of phi bar and phi, and the phase goes out, and obviously this is gauge invariant, okay?
And you can just do elementary algebra and compute the divergence of this current and check out that if you use these equations of motion, this is 0.
Yes.
Sure. You can just compute it by yourselves.
Yeah, sure.
We can discuss this afterwards.
Okay, but then there was this where I was here. Okay. So this was my question number 2, okay? And then now I come to this question, general relativity. So in general relativity, we have diffeomorphisms. If you make infinitesimal diffeomorphisms, you have 4 parameters, which are local. So it resembles like the gauge transformation, U1, when you had 1 parameter, which could be local, but you had only this parameter, it produced 1 current. So one may wonder, if we apply Noether's theorem, what do we get from general relativity? Do we get 1, and only 1, because we saw that changing a local to global will not enlarge the number of conserved currents? Do we get an energy momentum tensor? And what is the Noether current that you get from if you apply Noether's theorem to diffeomorphism? This is one thing on which there is a lot of confusion in the literature. I don't know if anyone dares answer this question.
Can I try? Well, you can get the energy momentum tensor, but that's not going to allow you to write straightforwardly a Noether current, because a Noether current implies a killing vector. So you have to specify a suitable killing vector associated to the symmetry you want to implement in, and coupled with the energy momentum tensor. Just this combination will allow you to get a Noether current.
Yes, that is correct.
Have a killing tensor. If you do not have a killing vector, so there is no Noether current. Yeah.
Yes, my question was precisely this. You do not have a priori killing vector. You have a general space-time, just general relativity in its pure form.
Well,
what is the Noether current?
Well, there is no, without a killing vector, there is no Noether current.
But one can use Noether's prescription to compute it. And my question was, what do we get from Noether's theorem?
Well, usually you get nonsense. I mean, and that's and that's a problem, because this nonsense has been spread by a gentleman which is pretty clever, called Albert Einstein. I mean, but that was mathematics that was unknown in his time. Okay, so it's not his fault. Okay, so.
Well, actually, I think, Oxford, that your first answer is entirely correct. There is no Noether current. But it is not because of the reasons, exactly the reasons that you are saying. First of all, because I'm calling this attention because I hear so often people say that the covariant divergence of the matter tensor results from Noether's theorem. It does not. Noether's theorem provides a current whose divergence vanishes, not whose covariant divergence vanishes. So you cannot get a covariant divergence of something from Noether's theorem. So the vanishing of covariant derivative of the initial momentum of matter does not arise from Noether's theorem. And in fact, you can get, even without space-time symmetries, you can get the covariant divergence equal to 0. So it is not related with Noether's theorem. Moreover, there is another point here. You see, when we compute the Noether current for a gauge symmetry, oops, sorry, I'm just trying to understand how does it works. Where was I? Here. Okay. And I was trying to use the pointer, but for some reason it is not working now. I'll not use it. So what I'm saying here is that the divergence of a vector density is proportional to the covariant divergence of the corresponding vector. That's the first equation. So you can get a divergence because the Lagrangian is also density with weight, with this weight of the, this integration weight of the metric. So when you derive the current, it's in this form that appears. And this is a covariant statement. So Noether's theorem is covariant. But for a tensor, that would not apply, okay? This equality is no longer valid. So in the bottom equation, the left-hand side is not covariant, while on the top equation it is. So for a gauge current, it's okay to get a current. But for a tensor, you get a problem, okay? Unless you are in flat space-time, okay? But if you are in a general space-time, that cannot be the case. So I had here question 3, where does covariant conservation of energy comes from? Okay, this was my third question, because it is not from Noether's theorem.
I have a question, sir. First of all, can you go back to just one more? Yeah.
Here?
Sure. And also the question that you wrote, it's from the Bianchi identities. I'm not mistaken. That's where the covariant derivative of the energy momentum tensor, right?
Yes, you can derive it from Bianchi's identity and the equations of motion.
But, sorry. This Felipe, this uses Einstein's equation, but
yeah, if you use Einstein's equation, obviously.
Yeah. No,
yes, if you use Einstein's equation plus the Bianchi identity, you get the conservation.
Yeah, but my question goes it's a bit smoother. That you mentioned that you don't know if you're assuming that you're on a very generic description where you don't know a killing vector, any killing vectors. But if that's so, then in order to do this procedure, don't you also have to assume that you have a chart that covers the whole manifold in order to get rid of boundary terms, in order to do the Noether's procedure? If I remember correctly, there was some discussion if you go full generality.
No, maybe you are confusing with another thing, which is Noether's theorem does not require any of these that you are saying. But when you want to compute the conserved charge, for instance, that's a different thing, because the charge is the integral of the charge density. Noether's theorem is a relation between the charge density and the current, okay? A local relation. But if you want to integrate and to find out the global charge, if the fields do not go far off,
if your chart doesn't cover everything. But then the question is, what are you computing then? If you don't have a notion to compare to, if another theorem is related to this global these charges are related to these currents, and you cannot ask what's on the right side of the equation, what are we really doing? That's kind of my point. Seems weird, that part.
I'm sorry, Bruno, I didn't understand your question. In the right side of what equation? What are you talking
about? When you write, how do you compute the charge? Then can you write that equation?
The charge, it should be the integral of the charge density.
Yes, and the charge density is the thing that you compute via the Noether's procedure, right?
Yes.
Yeah.
You find the expression.
You have a local description of that, but then what does that mean if you cannot compute its integral because there's no notion of charge? So are we really computing the symmetry? What are we doing? Right. That's kind of my point. Is that you
are talking about the case in which you cannot integrate and obtain a convergent quantity.
Yes, because you don't have boundary terms that you are canceling the actual. There's all these things that because we went on a full this general description, we lose, right?
No, actually, there is always a local meaning to conservation of a current, because it is not trivial that you can write to, let us say, in one dimension, just to make it simple. In one dimension, you have that the time derivative of a certain function plus the space derivative of another function must be equal to 0. So you can interpret one function as the flux and the other function as the charge density. And this is not trivial, because these functions must be local functions. They must depend on the fields only on that point and on that instant. It's not obvious at all that you can, in an arbitrary theory, find two such functions related such that the time derivative of one of them is equal to the space derivative of the other one, minus the space derivative. So this is not trivial. And if you can find such two functions, you can interpret them as the density of something and the other as the flux of something. So even if you cannot integrate the charge, it still has a local meaning. I don't know if this was your question.
Yeah, it's related. Yeah, it is indeed.
So, excuse me, I have to excuse myself because I'll have to leave soon for teaching. But let me make a point that may help in this discussion. Well, the first equality is true if the connection is Levi-Civita, right? So that means that the derivative of this conjugation, the square root of minus g and the current can be written as the covariant derivative of the square root of minus G the current, and you can put out the square root of minus G because this is 0 in the Levi-Civita connection, which means this is the so-called divergence theory. It's a mathematical identity. What is wrong in here? So, but this is true. If this is true for a current, so you can build a current out of the energy momentum tensor. So you do the job. The job is done. Okay. So the issue is how to build a current with the energy momentum tensor. And that's what I meant by the killing vector. If you have a killing vector, you can build a current and the job is done. Okay. So
yes, of course, because then you can contract this tensor with the killing vector, and you already
and
get a vector.
use the killing equation, which defines the key.
So, but my point was in general. Here, my point was
in general. So there is no way of doing it. So, and I'm afraid I have to leave because I'll be teaching soon. Okay. Thank you very much for the talk.
Thank you for your presence, Orfeo. It was nice to see you again.
Yes. Bye-bye. Thank you.
Bye. Okay, so but now actually I'm almost finishing. Here I'm mentioning this thing that Professor Orfeo said. The current associated with the diffeomorphisms cannot be a tensor. Einstein, Landau, and more authors, I think this was what Professor Bartolome was saying about Einstein. They found quantities, non-tensorial quantities, whose divergence vanishes within the general relativity, and that they claimed to be suitable candidates for energy momentum tensor. They are not tensors. That means that you can do a transformation and any of them, either Landau's or Einstein's tensor, can be made to be 0 at any point. Nowadays, people do not give much credit to these attempts by Einstein and Landau. But, well, I'm not going to talk about them because they are not true tensors, okay? But they, of course, do not come from Noether's theorem. So, to answer my final question, which was, where was it? What is the Noether current that comes out from diffeomorphisms? Because you can apply Noether's prescription to diffeomorphisms. And here is what Orfeo thought that it would give some nonsense, and it does not give nonsense. I made myself this calculation. You have here an action, Einstein's action, coupled to a Klein-Gordon field. You get these equations of motion that are familiar, Einstein's equations and the Klein-Gordon equation. And here, this T is the canonical one that comes from Klein-Gordon's equation, is here. And now, if you use Noether's prescription, you get this equation. There is a combination of the equations of motion which is equal to a divergence. So this is the tensor, this is the current. The point, of course, this could not give. This is not covariant, neither the left-hand side, you have here a connection, not the right-hand side, because as we just saw, it would need to have here a vector, not a tensor, in order to be covariant. But there is no problem in not being covariant, because the current that shows up here are nothing but the equations of motion, which are 0 on shell. So nothing comes out of Noether's theorem for general relativity. So Professor Bartolome was correct in his guess that nothing would come out of it, but maybe wrong in the sense that nonsense would come out. It is not nonsense. It actually gives the equations of motion, which are 0 on shell. This, in fact, I think this could be another question. I think this may be related to, once I worked in a Hamiltonian formulations, and I remember one result which was always present in Hamiltonian formulations. The Hamiltonian for a diffeomorphism invariant theory is always 0. I believe this is this may be related. The fact that we get, in fact, a current which is zero on shell may be related to this fact, but I don't know. This would be subject to another question. This is the last topic, that one that I told Professor Bartolome that I would talk in the end. Concerning the first question, whether we have a criterion to choose one tensor over another, we do have one. Here you have the energy momentum tensor. This is the standard part. I just put this in case this contains second order derivatives of the metric. I mean first order. So this is the general expression of the energy momentum tensor that comes out from Einstein's equation. In this, you can use whatever Lagrangian you use. You can add boundary terms. It always gives the same result. For instance, the two Klein-Gordon tensors that I showed you, it will produce only the first one of them. Okay. So this produces always one unique answer. Okay. Now, my doubt about using this criterion is the following, and this is kind of a philosophical question. Is energy a conserved quantity or the source of gravity? Because you see that energy shows up in both ways. Energy shows up as a conserved quantity, and it shows up as the right-hand side of Einstein's equation. But it does not need, this tensor does not need to be the same, particularly now that we are constructing theories that go beyond general relativity. The two concepts may not match. And personally, I think the first is much better. In fact, my physical intuition is that energy is a quantity that is conserved. Moreover, energy has been around for 2 centuries, people talking about energy, much before the creation of the general theory of relativity. Up until then, nobody knew that energy was the source of gravity. And nevertheless, people defined energy for almost all physical systems and always as a quantity that should be conserved for an isolated system. So I really tend to prefer the first definition to the second. And the same applies to electromagnetism, because charge shows up in the same 2 fashions. You can look at charge as the Noether current for gauge invariance, that is a thing that is conserved, or you can look at it as the right-hand side of Maxwell's equations. Again, the 2 are equal, but they need not to be. Electromagnetism is a relatively simple theory, linear. If you build more complex things, the 2 things may not be equal. You may not even have a right-hand side of Maxwell's equation to define as current. So this is the last topic. You remember that Professor Bartolome said there is a unique way to find energy. Yes, there is a unique way to find energy, but that's one way that I don't like very much. And I think that's it. Yeah, that's it. It's over. Thank you very much.
Okay, thank you, Professor. There's been many questions throughout the presentation, but we have time for some more. If anyone has any more questions. Thank you.
Can you show us that last slide again?
Okay, let me just.
I'm sorry if I'm being annoying.
No, that's great. Let me just try to. Okay. Okay, that's it. The last slide.
Yeah.
Oh, sorry. I reached the end and then it's
Yes.
okay.
Well, I'm thinking that what are the implications of giving an interpretation? Because both things appear naturally if you by the interaction Lagrangian. If you have a pure gauge theory and you introduce a charge, an electron, then your interaction term will always be a current times the contracted with the gauge field. And the same thing happens with with gravity, where if you introduce matter, then the interaction term will be the energy momentum tensor times the gauge, which in this case is the metric perturbation, if you linearize Einstein's equation. And so both things appear in the same fashion, which is in the introducing that interaction, that Lagrangian immediately defines what's the current and the electromagnetic and the stress energy tensor, and it immediately appears as both things, as the conserved quantity and the source of that field, even in the path integral formulations, what we do. So my question is, what is the interpretation or the interpretation of what do you get from saying, oh, it's this, it's a conserved quantity, that's the primary interpretation. They always appear in the same context, right?
In principle, you could write more complex Lagrangians using vector potentials and matter fields. And I am not certain that they would produce, first of all, that if the theory is gauge invariant, they would certainly produce the conserved current. And then you would have one definition of charge. Now, as to the other definition of charge, of what is on the right-hand side of the equations for the field, I'm not so sure, even if the equations, if you find it sufficient general Lagrangian, if you can write the equations in that manner as something that is on the left-hand side and which contains only derivatives of the fields, and something which is on the right-hand side. I'm not sure. I would have to think about it. But I can tell you that there is one student here which is watching this conversation, Miguel. He has been working with theories. For instance, in theories which are diffeomorphic invariants, but which are not general relativity. And for instance, he has approached certain theories where you construct the canonical energy momentum tensor in the fashion that you would get from general relativity, and then plug it in the action with cross terms with other, functions of the, in fact, in general functions of the space-time quantities. And then my question is, why would you call that the energy momentum tensor? Because it does not come out either from a conservation principle, nor as the right-hand side of some equations which concern only the space-time structure. Maybe Miguel can tell you better about these equations, but they don't have this structure.
Yeah, because it's not minimally coupled. That's
because they are not minimally coupled. Yes.
If there's no minimally coupled link, then I don't think there's even a notion of generating of charges generating this gauge field. I think that interpretation becomes very mixed up.
No,
Because you're using non-trivial couplings
If you have non-minimal coupling and the theory is nevertheless gauge invariant, then you certainly have another current.
It's weird to think of anything. Sure.
But so my point here was in which way we should look at these things. For instance, and this is for energy. In fact, we don't have in general relativity such a conserved quantity, in the sense that its divergence is zero. We have the covariant divergence zero, which is different. But still we have the source of gravity. In electromagnetism, we have both. But I am convinced, and I will try to construct some theory which is gauge invariant and which produces different results for the another current and for the right-hand side of Maxwell's equations. Those will not be Maxwell's equations, but some equations where you can separate one side with derivatives of the fields of the electromagnetic field and the other side which does not contain derivatives. I believe that is the understanding of the generator of a field. It's like in Einstein's equations. You have the left-hand side contains derivatives of the metric. The right-hand side does not contain derivatives of the metric. Yes. I believe that's more or less that's what happened in Maxwell's equations.
Yes.
So I believe that it's probably possible to build a theory such that you can separate the left and right-hand side. And the right-hand side you would interpret as a current. And then, but maybe this is not the same quantity that comes out of the Noether's theorem. And I don't know if I'm understanding your question is, if we have such good theories like general relativity and electromagnetism, where we don't have to question this, in electromagnetism it's the same quantity, why should we question such good theory? The point is that there are people like Claudio Gomes, Miguel Pinto, who are working in alternative theories to this.
I'm now for introducing any term, string corrections, non-minimal coupling. I'm down for that. I'm just interested in with the implications if you only see one thing as a conserved quantity and they're not appearing simultaneously through the interaction.
Yeah, but they do. My point is that they do not always. They do in Maxwell's electromagnetism, they certainly do. And actually, I'm not very fond of these alternative theories. I think electromagnetism is great and general relativity is great, and we shouldn't bother about it. But there are people who bother about it. So that's why that's why I'm questioning this, because in other theories, the two concepts may not merge. That's only because of that.
Yeah. Thank you. All right, then are there any more questions online? Maybe? Well, if not, then let's thank Professor Nuno Sá again.
Okay, thank you very much for your patience.
Thank you for the presentation.
And I liked very much this talk because it was very participative. I think, you know, in theoretical physics, often we ask questions to each other and we don't understand, and we think that we are saying something that is right and the other person is saying something that is wrong, because it's so often that we misunderstand concepts. What I'm thinking about is not what my, you know, the person who I'm talking about is the concept that this person is thinking about. And I found myself many times not being able to clarify ideas because sometimes our concepts are different, isn't it? It's not like engineering where you are going to compute something like, you know, the volume of which is an obvious thing. But it's nice. It's nice. It was. I did like I did enjoy your participation. Thank you very much.
Thank you.
Okay.
Okay, well.